Particle interactions, exchange bosons. So, when subatomic particles interact, they do so by exchanging virtual particles, or at least we can model them as if they're exchanging virtual particles. So, depending on your interpretation, a virtual particle is either a convenient piece of mathematics to help us solve equations, or it's an extremely short-lived particle that pops in and out of existence. The exchange of these virtual particles is how non-contact forces are felt. So forces between particles, whether they're repulsive or attractive, work by those particles exchanging tiny other virtual particles. So we can understand this in terms of an analogy. So let's imagine you had two ice skaters and they're throwing a ball back and forth between them. Every time one of them catches the ball, the momentum of the ball is going to push them back a bit and they're going to slide on the ice skates. And when they throw it back to the other person, that person catches the ball and they're going to slide backwards. So if you were watching these two ice skaters, but the ball was invisible, you'd see them mysteriously, without touching, push each other apart and repel each other. So that's just like the repulsive force between two charges. In a similar way, an attractive force, we could imagine that as two ice skaters standing back to back that are throwing a boomerang between each other. So when one of them catches the boomerang, it pushes them backwards and they move closer to the person who threw the boomerang. And then when they throw it, the same happens again, and the two people end up mysteriously moving closer and closer together if you couldn't see the boomerang. So there are four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Only charges feel the electromagnetic forces, so neutrons and neutrinos don't. Only hadrons feel the strong nuclear force, that's only particles made of quarks feel the strong force. All particles feel the weak force, and all particles feel gravity. We can model each force as if it was an exchange of these virtual particles. Now the virtual particles have different names. Sometimes they're called exchange particles, sometimes they're called gauge bosons, because each of these can be described through its own gauge field. So the strong nuclear force, which is the strongest of the four fundamental forces, that has an exchange boson which is either a gluon or a pion. The electromagnetic force exchanges virtual photons. The weak nuclear force exchanges W particles or Z particles, and gravity we don't know, so we just give it a placeholder and say whatever that particle would be, it would be a graviton. So particles exert forces on each other by exchanging these gauge bosons. And whether a type of particle can feel a force or not depends upon which gauge bosons it can exchange. So only hadrons feel the strong nuclear force because only hadrons can exchange gluons that carry the strong nuclear force. Right. Leptons can't exchange gluons, so they can't feel the strong force. Now the mass of an exchange particle, a gauge boson, determines how far it can travel. Right? This is the range of the force. So the more massive a gauge boson is, the shorter the distance it travels. So that's one of the reasons why the weak nuclear force is so short range, because its exchange boson, the W boson, has a mass that's 100 times bigger than a proton. So W bosons are very short range, so the weak force is very short range. And the reason for this is that you need to borrow energy to create the exchange particle. So through Heisenberg's uncertainty principle, we know that if we borrow a certain amount of energy, that limits the amount of time we can borrow that energy for. The more energy we borrow, the shorter the amount of time we can have it for. So if we need to make a massive particle, it has a lot of rest energy through the equation E equals mc squared, where c is the speed of light and m is the mass of the particle. So we need to borrow more energy, which means it can only exist for a shorter time, and in that time, therefore, it travels a shorter distance. By contrast, a photon has zero mass. The electromagnetic field has infinite range because virtual particles can live forever, virtual photons can live forever, and they can travel in principle an infinite distance.